Righto. Okay. Yeah. So let's go ahead and start here. So there's one conceptualization that I'd like to work on here, and it boils down to this. So last time I left you, we were working on the right-hand rule and using the right-hand rule to determine the direction of a magnetic field based on the current. And I said, oh yeah, let's not worry about the top part of the problem. All we did was that we dealt with the magnetic field due to a current that's coming out of the board and the magnetic field of a current going into the board. Okay? So now what I want to kind of address this question that we have here. But what I want you to now think about is, rather than this being like a straight line going out of the board or a straight line going into the board, I want you to think about this as being the cutaway section of a loop of wire. So imagine for a second that this loop is coming out of the board and it goes in, and it's a circular wire that we're viewing edge on. Okay? So if I could see if I can draw that, again, it's a cutaway view, but I wouldn't be very, okay, I'll attempt it. We'll see what happens. Ah, no, we'll see what happens here. Yeah, imagine that this is a loop of wire where we have just taken a slice, but the current is running kind of like this. Right. So out of the board, into the board, and it's all right, okay. So question for you. What's the magnetic field going to look like for that loop, that current carrying loop of wire? All right. Go ahead, talk to me and get an idea. So this current carrying loop of wire, what's the magnetic field going to look like? I'll start there. And draw it down. You can dance a little. No, I don't know how they're. Is that right? I mean, I know this is the Charlie Brown. I mean, this is all the rage. Oh, no. It's the jumping. I can't get the jump timing right.
Can't help you.
I've been working on the floss, but I've been told that it's just not right. I've been told I'm too stiff.
So yeah, the middle down.
Usually I think of the thumb, that'll work. I usually think of the thumb going in the direction of the current and curling your fingers in the direction of the magnetic field. Is that what you were doing, or were you telling?
I'm not even sure anymore.
Oh, okay. There's two ways to go at it, but I told you run the current in the direction of your thumb, and then your fingers curl around to the direction of the magnetic field. Okay, yeah, I'll buy that. You got an idea? I mean, for these cutaways that we've got, we worked on this on Wednesday. You can think of, okay, well, dot means that it's coming out. So I run my thumb in the direction of the current, and my fingers go in the direction of the magnetic field. So you can think of the magnetic field as going something like counterclockwise for that segment of the wire. Of course, over here, thumb is going in, right? Current is going in, that's what the X means. So we can think of running our fingers around that wire, and so it looks clockwise. I can draw those in. Something like this. Yeah.
I'm just still confused by the difference between the magnetic field and like force and all the different like.
Oh, we haven't talked about the force yet. We're still just on the magnetic field.
What is the magnetic field? I know that you've got your north and your south. That's about it. And the north goes out and south goes in.
Yeah. Yeah, that's fine so far.
But then that little dot and cross.
Oh, yeah, so
I know
this,
that
right,
north is in and this is out.
yeah, so this dot and this cross are supposed to represent the direction of the current. So yes, I have not labeled, this is the current traveling out at you, and this is the current traveling into the board. So right now, I'm just thinking of a wire that physically carries a current going like this in a circle. And I want to know, what does the magnetic field look like due to this current carrying circle?
And so then how did you get those little images?
The right-hand rule. So so I've got the current carrying wire. The right-hand rule will tell me what direction the magnetic field is due to this current carrying wire. And so if I run the current out of the board in the direction of my thumb, then my fingers will give me the direction of the magnetic field due to that piece of the wire. And the same thing, the current is going into the board. Because of that current, there is a magnetic field that is being generated that goes clockwise around that wire. Is that good?
Yes.
Okay, so that's all I'm drawing in here is, hey, the magnetic field due to those two separate pieces of the wire. Is that okay so far? Just trying to. Now you can imagine I just did a cutaway view of those two pieces, but remember this wire is going, right, there's a circular part to that. So I think do I have that? Yes. Shamelessly stolen because I am not good at drawing. Right, if you had this wire, if you think of this gray piece as being the wire, where current is flowing out, rolling in, going in, you should end up with this kind of magnetic field. Where in the middle, it's going straight up, right? It loops around and comes down and then goes back in from the bottom. Yay, nay? Now we can actually ask the question that I have at the top. So, right, like I should break this into like 3 different slides. Like, let's do this first, then let's do this. Now let's compare it. Okay. If I look at the magnetic field of this current carrying loop. So forget about how the magnetic field is being generated. Let's just look at the magnetic field. If I wanted to replace that current carrying loop with a bar magnet, which bar magnet would give me the exact same field? Which orientation of the bar magnet will result in a magnetic field that looks like this arrangement here? And let's see, Cassie mentioned it. It goes from magnetic fields emanate from which pole, go to which pole? North to south. So which of these 4 bar magnet arrangements would produce the exact same magnetic field in terms of what it looks like? What say you? The first one, I agree. Right, the magnetic field runs from north to south. So you could say, okay, well, here, we'll go here. This runs north to south, so it should look something like this, although I can't draw. Good gravy. Yeah, I'm really off today. Let's try this again. Right, it runs from north to south. That is exactly in the opposite direction of what I actually see, right? This over here, the magnetic field's going that way. This arrangement, it would be going this way and down. That's not it. And of course, left and right, you can see right away, okay, well, it's not going left to right, you know, like this. No, it's up and down. So that's not, yeah, I agree. So based on just the magnetic field, so again, I was saying, I don't care how the magnetic field's generated. What I care about is which arrangement gives the same magnetic field. Now I put this in because this is kind of how we think about it. In reality, it's a current carrying loop that generates the magnetic field. But we could conceptualize it simply as a tiny bar magnet. From the standpoint of the magnetic field, those two are the same. A tiny current carrying loop generates the same magnetic field as like a tiny bar magnet. Reality, tiny current carrying loop. Conceptualization and modeling, bar magnet. Is that okay so far? So let's go back to chemistry. Why is iron a really susceptible material to be magnetized? Unpaired electrons. You could conceptualize an unpaired electron in the atom as being a tiny current carrying loop. The orbit of the electron around the iron nucleus, you could conceptualize that. Now I'm thinking the Bohr model of the atom. Okay. But it still works out if you want to take the quantum, SPDF shells. Okay, it still works out the same way. Okay. You have an unpaired electron that's circulating in the atom. That's a tiny current carrying loop. And we can conceptualize that tiny current carrying loop as just simply a little bar magnet. This should also give you an idea of why it's impossible to separate the North Pole from the South Pole. Right? You have a tiny current carrying loop that generates a magnetic field that looks, you've got that figure. Well, how do you cut that in? I mean, I don't even know what it would mean to cut that in half or to try to separate. Right? It's one piece. You don't get you can't separate it out. I don't know if that makes sense or not. Like, how do you have a tiny current carrying loop that doesn't have an up without a down? Right? If you have the field going up this way, it has to come in from the bottom. Like, I mean, how do you can't separate the North Pole from the South Pole. Sorry, that gets a little metaphysical there, but the idea still holds. Materials that can be easily magnetized tend to have unpaired electrons, i.e., a lot of circulating current at the atomic level. Yeah.
That unpaired electrons run in opposite directions because they cancel each other.
Yeah, there's some other stuff like, so not only do you have the orbit of the electron, but you also have the spin of the electron. And so you have spin up and spin down, and that will, that's like having the electrons orbiting in the spin up and spin down can cancel, so it can decrease the overall effect, I guess is the best way to say it. So you have the spin motion, but you also have the orbital motion. And if you can get unpaired electrons, you've maximized both the orbital and the spin, and so it tends to be easier to magnetize. So if you have paired electrons, that decreases a little bit, and then The S shell has 0 angular momentum, is that right? Who's been in P-Chem? The S shell is L equals 0. Okay, let me think. S is a sphere, and so you have no preferential direction, and so the angular momentum is 0. Yes.
Affected by like the mass or something that's moving.
I'm sorry?
Is momentum affected by the mass or something that's moving?
Yeah, the angular momentum, but yes. Uh-huh.
Build S orbital has less mass than a build S orbital.
Well, the S, okay, so if I think about quantum, so the S orbital we usually conceptualize as a sphere. There's no preferential direction, right? Spherically symmetric means that there's no preference for the orbital direction. So you have things going like this, but you also have things going like this. So there's no preferential direction, and so the overall average current tends to be 0. Because for every electron that you have going like this, there's another one going in a different way that cancels. Of course, at that point, we're talking electron clouds, not actually electrons, and there's some other stuff going on there. But to go back to the original point, yes, you want unpaired spins, and if you can, you want non-s orbitals. You want p's, d's, f's. Which again goes back to iron. You notice that iron has a lot of unpaired electrons in the d orbital. So you have a high current, basically. Unpaired electrons, and they're all circulating in these asymmetric orbitals. And if you got that, then you basically, okay, how do you magnetize objects? Questions so far? So rather than thinking about electrons running around the atom, you can just think of each atom of iron as being a tiny bar magnet. From the standpoint of the magnetic field, those are the same. Incidentally, that's also called a dipole field. You notice this is the same kind of looking field as if you took a positive and negative charge and drew the electric field. Sorry, I put a throat lozenge in, but my throat's a little sore today. I don't feel sick otherwise. It's just like, felt good, but I think I'm just 3 hours of talking and just, no. Shouldn't talk with stuff in your mouth is what it comes down to. I feel like I'm slurring my words, but I don't want to swallow this thing either. There we go. That takes care of it. How many licks does it take to get to the center of a Tootsie Pop? 3. No, it's literally, that's the commercial. Mr. Owl, how many licks does it take to get to the center of the Tootsie Pop? I don't know, let's see. And you go, 1, 2, 3, and then you write it. He goes, 3.
He says the world may never know.
Yeah, and then it says, yeah. How many licks? Yeah, that's good. Yeah. The owl says 3, but then the world never knows. Yeah, that's a good point. I forgot about that part.
You did it, you didn't like it.
Yeah.
Okay.
Oh, okay.
The average is like 570 or something.
Oh, I don't know. Yeah. I'm just glad that you guys know that reference. That makes me, oh yeah, Kool-Aid's here. I don't know if that one makes sense. The Kool-Aid commercials, yeah, I used to have the guy busting through the wall. Hey, Kool-Aid's here. Oh, that's good to know. Okay. Yeah. So yeah, you could think of this tiny current carrying loop as being a bar magnet. So yeah. Okay. We'll come back to that, but yeah, how do you actually magnetize objects? That we'll come back to that idea, that conceptualization. So the other thing that I wanted to talk about, the book gives you an equation for the magnetic field due to a wire. In fact, maybe I should write that down. I apologize, I don't have that in my notes. If you want to know the magnetic field of a wire, let's see, where's the best place to put this? Okay, solenoid, that's a bad place. Okay, well, I'll just write it right here and so you have it. The magnetic field due to an infinitely long wire is given by mu naught I divided by 2 pi. And I don't know, do you want me to put the D here or should I put an R in here? It's the distance to the wire. You want D or R? My gut tells me R, which means I should probably use D. So I'll put D in here. There. So this is supposed to be distance to the wire. And again, mu naught is that permeability of free space. I is the current that's carried by the wire. Now that's one object that, I mean, straight out, I'll just give you the equation. If you get really interested, we could probably derive it, but I would have to do it numerically. So in other words, I'd have to open up my Excel, I'd have to program everything in, and then we'd have to do a bunch of calculations, and I would show you that you get the same answer. If you're really jazzed about that, stop by the office. I don't know how long it'll take, maybe an hour. I don't know for sure. Or you could just say, okay, here's the magnetic field due to a long current carrying wire, and I'll just keep going. Yeah, that's fine. So the other object that I want to give you the equation for, and I hope I got this right. I better make sure I got the wire right. U naught I enclosed. This is the circumference of the circle. U naught divided by, yeah, I think we're okay. I just wanted that 2 pi d is not by accident. That's the circumference of the circle. You don't need to know that, but that's why it pops in there. So, okay, but there's one other object that I want to give you the magnetic field strength for. And the reason that I'm taking the time to do this one is because this one is the exact analogous, this is the equivalent to the electric field. So capacitors are to the electric field as solenoids are to the magnetic field. So I thought I should at least give you a conceptualization of how the solenoid works. So we'll sit down and get the conceptualization, and then I'll just hand you the equation. Say, here's the equation that gives you the magnetic field strength inside a solenoid. Cassie, you had a question?
You said the capacitors are.
Oh, yeah, capacitors are to the electric field as solenoids are to the magnetic field. So, for example, you can tell me what I should say this. What can you tell me about the magnitude of the electric field between 2 plates of the capacitor? The parallel plate capacitor. What can you tell me about the magnitude of the electric field? Two infinite plates. It's constant. The magnetic field, or excuse me, the electric field inside a parallel plate capacitor is constant in magnitude. Second question. Roughly speaking, what's the value of the electric field outside the capacitor? Inside it's constant, non-zero. How about outside the capacitor plates, roughly speaking? Zero. Right? The electric field due to the negatively charged plate cancels the electric field due to the positively charged plate outside of the capacitor. So outside the capacitor, it's roughly zero. Inside the capacitor, it's some constant non-zero value. Inside the capacitor plates, what can you tell me about the direction of the electric field? Changes, not changes?
No.
Not changes. So there's 2 things. The magnitude is constant. It's the same strength everywhere, but also the direction is the same. And we kind of drew that, right? We do a parallel plate capacitor. Excuse me, I'll go to another side here. You do a parallel plate capacitor. You put a charge positive Q and negative Q. Excuse me, that's a bad cue. And we usually think about the electric field lines as running from positive to negative. Constant value, same direction. And it's not by accident that I didn't draw in the electric field lines outside of that arrangement. Yes?
So could we tell the direction north and south, or like the last one? I'm not sure.
Could you tell the north and south direction? Yeah, the magnetic field emanates from the North Pole and goes towards the South Pole.
So that is an actual.
Yeah, you could think of, so we will kind of ignore what's going on right there, but you could say that's the North Pole and that's the South Pole. It emanates from the North Pole and it'll go towards the South Pole. I'm sorry? South to north. Or, sorry, I'm not quite sure. Say it again, Isaiah.
It looks like it's going the opposite way.
Yeah, it's emanating from the North Pole, and it's going into the South Pole.
Okay.
Yeah. Yeah, and same, sorry, the arrows are small here. These are arrowheads. They're going this way. So emanating from the North Pole and going towards the South Pole. So by that analogy with the electric field, inside the solenoid, what can you tell me about the magnitude of the magnetic field? Again, I said the capacitor is to the electric field as the solenoid is to the magnetic field. So if you have some ideas about capacitor and electric field, let's apply those same ideas to the solenoid and the magnetic field. So for example, inside the capacitor plates, the electric field is constant. Inside the solenoid, the magnetic field is constant. Between the capacitor plates, the direction of the electric field is constant. Inside a solenoid, the direction of the magnetic field is constant. Outside the capacitor plates, the electric field is roughly 0. Outside of the solenoid, the magnetic field is roughly 0. So all of these things, and the analogy applies. Just take what you know about capacitors, apply it to the magnetic field. Now, conceptually, why is that happening? Right, so we talked about charging up capacitor plates and yada, yada, yada. So conceptually, what's going on with the solenoid? So up here, I have a solenoid, just shamelessly stolen from some, website. Yes, it looks like a spring. And what we're going to do, let's go ahead and, well, I've got current going in. Let's go ahead and I'm thinking about this top piece right here. Okay, so if I do a side view, that's current going into the board. Okay, so if I think about taking the solenoid and slicing it, I've got current going into the board. Quick! Based on the current going into the board, what direction is the magnetic field due to that small piece? Imagine taking a solenoid, slicing it, the current's going into the board. What direction is the magnetic field due to that little piece? Clockwise. Thumb in the direction of the field, or the current. Fingers curl in the direction of the field. So we've got clockwise. Due to that tiny little piece right there where I've circled. So you've got some sort of clockwise doodad. What do I do next? Yeah. Now the current keeps going, right? I send it up, it's going in, it keeps going around, keeps going around, keeps going around. Then right here at the bottom, what direction is that current now going? Imagine it's going in, it comes around, and now at the bottom of that loop, it's coming out at you. And imagine it's coming in at the top, goes around that backside, and now it's coming out at you. So down at the bottom, what direction is the magnetic field due to that current that's coming out of the board at you? Right-hand rule. And I'll draw that one in. But wait, there's more. Because this isn't just a current carrying loop, right? It's a current carrying spiral. Which means I can keep following it. That current comes up in the front, comes up all the way to the top, and now I get here, that second top piece. And so I have another, oops, there we go. So I have another location where, again, it happens. It's going into the board. Of course, then I go to the bottom, and it's coming out. And as I go down the line, because it's a spiral now, as I go down the line, I will continually get places on the top where it's coming out, and on the bottom, on the top where it's going in, gives me a clockwise magnetic field. On the bottom, it's coming out, gives me a counterclockwise magnetic field. I guess a different way to think about this is think of it as a bunch of current carrying loops all stacked on top, crushed together. Right? We did for one loop, now we just think of doing a bunch of loops that are stacked on top of each other. Yay, nay? Oh, I got a question. It wasn't a question. Panic. You never notice how excited teachers get when you're like stretching? No? Oh man, I'm just stretching. Oh. Question. Two adjacent wires. What's the net magnetic field right there? Zero, right? You've got one, the magnetic field from the right-hand piece cancels the next one, so you end up with these pieces canceling. Right? You could think of these canceling. And it's the same thing down on the bottom, right? You've got these fields, they're pointing in opposite directions. You can kind of think of those canceling. You notice inside, right here, sorry, I probably deleted in a second here, but you notice right here in the interior, what's the direction of the magnetic field, roughly speaking? Yeah, you notice that you don't get cancellation, right? The top wire gives you a field going to the left. The bottom wire also gives you a field going to the left. And so you don't get any cancellation. You end up getting some sort of superposition going to the left. Now, outside of the wire, I don't have it. You say, well, what happens? What do I do here? Oh, yeah, excuse me. I should just follow my presentation view. So let's get rid of some of these arrows. Get these guys, get rid of those. All right. Hey, these cancel out. Now, the other piece that I should draw in here, let's look at these pairwise ones for a second. So we got rid of these by considering adjacent wires left and right. Let's go ahead and think about this for a second, these two wires. Now, I don't have it drawn in, but let's think about the bottom wire. It's creating a magnetic field, and I'll draw it in red up here, that goes to the left, above the solenoid. I didn't draw them in, but this wire creates a magnetic field going to the left pretty much everywhere. I should draw it up here, I could keep going. So this left magnetic field due to the bottom wire at this location cancels roughly speaking, that blue magnetic field going to the right due to the top wire. And similarly, down here, we have the red magnetic field, the red magnetic field going to the right, and I'll swap it to blue. I should have done different colors for these. I'll have to change that. The top wire gives a field going to the left, and so beneath the solenoid, those fields will cancel. Again, that's going into that idea that the magnetic field inside the solenoid is constant, pointing in one direction. Outside the solenoid, it should be 0, roughly. Now you know that there's going to be a slight magnetic field there. It's slightly closer, up here, it's slightly closer to the top wire, so the top wire's magnetic field strength is going to be slightly larger, so it doesn't quite cancel. Let's deal with spherical cows in space, if that's okay with you. Right? Let's deal with spherical cows in space. We will assume that the magnetic field outside is 0. And the only place where there is a magnetic field is inside. Get rid of that. And furthermore, while we're at it, we will assume that the solenoid is infinitely long. We will assume it is long enough that we don't have to worry about I think I saw it for the capacitor as well, the fringe field. Right? We will assume the capacitor plates are so large that we don't see the edges, so we don't have to worry about the fringe field. We will assume that the solenoid is so long that at the endpoints they're far enough away we don't worry about the fringe field. Sorry. I don't know, it's like after a year of wearing these things, like my ears start hurting after a couple hours. I don't know. You guys like getting like chafed on your ears from your mask? Yeah, okay, so it's not like, I mean, somebody said, yeah, just get a pair of cheap glasses and you feel the same thing. Like, man, never buy a pair of cheap glasses. This is driving me nuts. Someday. Someday over the rainbow. Good? No, I mean, this isn't the bulletproof. I'm just trying to give you a heuristic argument. How does this thing work to give you a constant magnetic field? It's a current carrying loop. You have the magnetic field of adjacent current carrying loops canceling each other out, except in the middle. I don't know if I have, do I have a better, yeah, there you go. So if you really wanted to constant inside, then you've got this fringe field, but basically 0 on the outside. That's a really crappy picture. Wow. You guys should yell at me for just shamelessly stealing that from the internet and blowing it up. I'll try to Photoshop it sometime. Maybe take out some of the Sorry. Something's buzzing somewhere. Turn that off. Excuse me, I thought I had the ringer on silent. Turn it on. There we go. No, it won't bug us. So let me give you the equation for the field strength. Did I write it down here? There we go. So if you want to know the strength of the field inside the solenoid, it is again a geometric quantity. Here, mu naught, as you know and love, N, capital N, the number of loops in the solenoid. And capital L, the length of the solenoid. So the number of loops in the solenoid and the length of the solenoid. That will dictate how strong the magnetic field is. Of course, you also have I, the current that you run through. Okay. but N over L. Now, sometimes it depends. When you run across this, sometimes you'll be told the number of loops and the length of the solenoid. Sometimes you are given, rather than the number of loops and the length of the solenoid, you might be given what's called the turn density, the number of turns per unit length. So sometimes rather than seeing as total loops divided by total length, you might see it as, nope, I didn't put it in here, so I'll draw it in. You might see it as the magnitude of the magnetic field is given by mu naught little n times I. So where little n is the turn density. Number of loops per unit length. And in reality, when you run across a solenoid, like in the everyday world, if you went out and tried to buy a solenoid right now, chances are it will tell you the turn density. Usually because it's like this really fine copper wire and they wrap it so many times, it's a pain in the rear to count. You just say, okay, well, I'll give you the turn density, the turns per unit length. In a 1 meter span, you have 100,000 turns, 100,000 loops. Yes?
So would that just be N divided by L?
Yes. Little n is big N divided by L. So that's why it's giving you the same information, it's just how it's presented. Yeah, I can give you the total mass and the total volume, or I could just give you the density. Yeah, if you're thinking mass density. Questions? Other questions? Yeah.
So like capacitors store charge, is this store anything?
Yeah, good. Capacitors operate by storing charge, and because of that, you generate an electric field. Yeah, that's a very intuitive comment. Yeah, what does the solenoid store? And this will tie into the next chapter, actually. Yeah, this will tie into the next chapter. What do solenoids store? It's very interesting. How do you generate a magnetic field? Current. Solenoids are a way of storing current momentarily. So yes, it's very insightful. Solenoids will store current. In other words, if you are running a current through a solenoid and you decide to stop running current through the solenoid, for a brief period of time, the solenoid itself will run a current. And you've probably witnessed this, although you don't recognize it. So here's one place where you probably witness this. You ever do the bad thing to an electronics? I mean, let's say you want to unplug a piece of equipment, electronic equipment. What should you do first? Turn it off. You ever be bad and just unplug it without turning it off? You're vacuuming, and just yank the plug. Or maybe you don't even need to do it. You're vacuuming, you get too far away, and all of a sudden the plug comes out and the vacuum dies. Right? That's hard in your electronics. And you don't usually want to do that, but sometimes we're all lazy. What happens when you do that? You ever notice? You're sitting there vacuuming, you pull the plug out of the wall. You ever notice what happens? Or sometimes other way too. But usually I notice it when you unplug it. What happens when you unplug it? And it's still running. Fizzles. You ever see a little zap in the wall plug? You ever get a little spark? Yeah. What's going on there? I've disconnected. I've introduced a break in the circuit, and that little spark is the circuit still trying to stay connected. What's driving that current? I've disconnected the wire. Why is there current still being driven through the circuit? Somewhere in your circuit, you've got a solenoid that's trying to keep the current running. So for a momentary second, when you're unplugging it, the solenoid is using its quote-unquote stored current to kind of try to drive it still. Yeah. This is nice also. This will tie into a subject called Faraday's law, which yes, we will talk about because it is the way that's how we keep the lights on. So of the things that I've tried to chop out, Faraday's law is not one of them, because that's how basically aside from photovoltaics, everything else generates electricity using Faraday's law. It says, shoot, that's so important that we got to discuss it. Yeah. So, you ever notice as well, let's see here, do I have one? No. Okay, to be continued. You know those monitor cables, you ever notice that little cylinder on the line? Like if you have a monitor that connects to your computer, there's a little cylinder on the line. Yay, nay? I'll also see if I can bring one in. Okay. That cylinder is another solenoid. And so if you ever have an electrical line that has like a cylinder on it, that's a solenoid somewhere. Okay. And they put that there because not only does it store current, but it also, for lack of a better word, I'll say it dampens the current. If you get a spike in the current down the line, the solenoid will say, whoa, 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 hold your horses. Or if you get a sudden drop on the line, the solenoid says, here's a little extra current for you. It keeps it going. Yeah. No, that's very insightful. Yes, the solenoid will store current. I'll put that in quotes. So it'll store. Store is probably a misnomer. I will say that it wants to keep charges moving. So if the current drops, it will try to keep the charges moving at the same rate. If the current spikes, it'll try to keep the charges moving at the same rate. Yep. Yeah, other questions? I don't remember what I had yet. Okay. So that's all I have to say about the magnetic field. We have Orsted's experiment that tells us charges create magnetic fields. Moving charges, moving charges. And then we have a couple of, okay, well, how do we get the direction of the magnetic field? And what are a couple of arrangements of currents that give us magnetic fields that we can easily write down? So long straight wire, you have the solenoid. Those are probably the two easiest arrangements to have. Right? And frankly, once you get past that, it becomes particularly arduous very quickly, right? Because of the law of Biot-Savart and some other calculus stuff. Okay? So it gets arduous really quickly. Most of the time, even nowadays, like I'm thinking, you get very particular arrangements that you can solve by hand, and everything else you go to a computer to do, okay? Because it's just too hard to do otherwise. So really, that's all I have to say about the magnetic field and the generation of the magnetic field. But we should talk about the magnetic force. So Oersted said moving charges create magnetic fields. And we know that magnets attract and repel. So moving charges create magnetic fields, and magnets attract and repel. So one of the logical conclusions of this is that magnetic fields should exert a force on moving charges. If a moving charge generates a magnetic field, and magnets attract and repel each other, then a magnetic field should exert a force on a moving charge. And indeed, that's the case. Right? That's the logical, yeah. Moving charges should be affected by magnetic fields. Or maybe I shouldn't say should be, I should say are. Moving charges are affected by magnetic fields. And this is where you'll see a lot of stuff. Like this is how you filter out a charge to mass ratio. And you don't usually tend to do that with the electric field, you do it with the magnetic field. And yeah, it has some really spiffy applications. We have a velocity filter, we'll have a sorting magnetic field. Oh, you could get, I hope you guys don't yell at me for this one. I'm always hesitant because it's really interesting, but it's also kind of weird. Have you ever heard of a railgun? Okay, I've got an image of a railgun here. So it's a really cool video. Unfortunately, well, again, somebody should yell at me, I guess, because, well, okay. I mean, some of this spiffy stuff comes through like naval research. So it's like they have railguns for a very nefarious purpose, but they're kind of cool. It's a cool application of physics. And so, yeah, anyway, okay. So let's get at that. I should give you the idea or the equation first of all. Now, you want to get the direction of the force. I mean, force is a vector and a magnitude. So how we get the direction of the force? I do solemnly swear to use my right hand. Okay. So first off, again, so not only do we use the right hand rule to find the direction of a magnetic field produced by a moving charge, but we will also use the right hand rule to find the direction of a force that a magnetic field exerts on a moving charge. So we can double. Right? Moving charges create magnetic fields, the direction of which we can find with the right hand. Okay? Magnetic fields exert forces on moving charges. The direction of that force we will also find using our right hand rule. Shoot, I can't remember if I have. Okay, so that's how we'll find the direction. The magnitude is given by, you've got several different ways of doing this, all of which should look familiar, right? You can say, I take the charge that's moving and multiply by the magnetic field strength. Of course, right here I have perpendicular. I need to take the component of the charge's velocity that is perpendicular to the magnetic field. That's one way of doing it. Or, conversely, I could take the speed of the charge and multiply by the perpendicular field. The field perpendicular to the direction of motion. Or, I could take the magnitude of both the speed and the magnetic field and multiply by the angle between. And you should yell at me because this last one is missing a Q. If I could, okay, I'll put the Q in over here. This last one is missing a Q, which is shameful. Now you've seen this before, like R perpendicular to F, or F perpendicular to R, or R times F times the sine of the angle between. And it's the same pattern that you've seen with torque. It's the same pattern that you've seen with angular momentum. Some sense, I don't really have very much more to give you there. That's like straight up definition. The one thing that I will say, a charge times a speed, you could recast that. So a moving charge, instead of talking about it as this charge moving at a speed, you could talk about it as a current. So you could recast this as this if you want instead. Sorry, I got like a piece of fuzz in my mouth. No, I didn't get it. Oh, no. Man, at least I was consistent with dropping things. Because in the second expression, I'm still missing the I, the current. There we go. So you could think of it as a separate charge moving at a speed, depending on what information you're given. So this would be like, you send an electron through a magnetic field. Then you probably want to do this. But on the other hand, if you have something like a current carrying wire, then the second expression might be the better way to go. Okay. So which expression you use depends on, are you given a current and a wire, or are you given like individual charges and speeds? Either one should be okay. in terms of solving the problem. Directions. To get the direction of the force, let's say you're dealing with this top situation, where you're given the speed or the velocity of the particle and you're given the direction of the magnetic field. Shoot, how do we do this? Is there a shortcut? I don't think there is. Sorry, I'm just trying to run my, there is none. Okay, just trying to think of the shortcut and I can't find one. So I'll just give you the full blown one instead. This is still the right hand rule. You have to use your right hand. Right? Here's how we're gonna do it. Fingers in the direction that the charge is moving. Okay. Palm in the direction that the magnetic field is pointing. Right? So for example, let's say that I have a proton moving to the right and the magnetic field is out of the board. And we'll call this a proton. Okay. So fingers have to be in the direction of motion. The palm has to be in the direction of the magnetic field. The other way to say it is you point your fingers in the direction of motion and curl your fingers in the direction of the magnetic field. That'll work the same way. Because on your palm, you know, your hand, your fingers curl in the direction of the palm. Okay. So first one, speed of the direction that the particle is moving. Palm pointed in the direction that the magnetic field is pointing. So in this case, I have the magnetic field pointing out of the board. Your thumb gives the direction of the force. Okay. So let's say that again. Fingers. Okay, I can't. Fingers. Fingers, palm, and your force will be your thumb. There we go. Or if you prefer, if it's a single charge moving through a magnetic field, fingers, palm, and thumb, same thing. You could say the direction that the current is flowing is your fingers. The direction of the magnetic field is your palm. And again, the thumb gives the direction of the force. But I say when you're doing physics, you got to do some Tai Chi. Like you find yourself doing this at some point. Yeah.
What is delta?
The length of the wire. Yeah. And if you notice, if I take a current and multiply by a length, I end up with the same units as if I took a charge multiplied by a speed. Yeah. Mm-hmm. Yeah, the length of the wire. Incidentally, if you're asked to find the charge of the force on a current carrying wire, it might ask you for the force per unit length. So just go and look, when you're reading a problem, make sure, is it asking you for the force or is it asking for a force per unit length? So it might say, it might not specify how long the wire is, but it might ask for a force per unit length instead of a force. Yeah. Well, here's a good question. Let's think about a proton moving through a magnetic field. Okay. Say proton's moving to your right, just like I have it drawn. Let's say the magnetic field's out of the board. The force that the magnetic field exerts on the proton, how does it compare to the direction of motion of the proton? It's perpendicular. Right? The force is going, the motion is to the right. The force is down, perpendicular. Good so far? Oh yeah, I got another question. Actually, maybe I have it there. Let's do this. How about this one? Let's say that the proton is moving down, what I've labeled as negative z direction. And let's say the magnetic field is out of the board, what I've called positive x. What direction is the force acting on the proton due to this external magnetic field? Go ahead. Talk to your neighbor, get an idea. Go. Get an idea. I gotta do it too. Let's see. Yes. Feels weird like this. Fingers in the direction it's moving. Palm in the direction of the magnetic field. Thumb gives you the direction of the force. So for this arrangement, the force is in which direction? Negative y. Yeah. Good, good. I gave you the axes here, so I just wanted to make sure that you could, yeah. So it's in the negative y direction. Also perpendicular to the motion. Right? The particle's moving in negative z, the force is negative y, it's perpendicular. So here's a question for you. When the force is perpendicular to the direction of motion, what trajectory will you get? If I take this particle, this positive charge, and it's moving through a magnetic field, what trajectory will it follow? What path? You can describe the path to me when the force is perpendicular to the direction of motion.
Path of the current.
What's the path of the current? But what's the path look like? When you have a force that's perpendicular to the direction of motion. Yeah, this is why I want to make sure I can ask. Yeah. You probably say, oh no. Say, oh yes. No, yes. Question. Object's moving to your right. And you exert a force to the right. What changes about the object's velocity? What happens? Does the direction that the object move change? No, what does change? Not the direction that it's moving, but
Acceleration.
it's accelerating. Yeah. When the acceleration is parallel to the direction of motion, the speed goes up. How about when the force is anti-parallel to the direction of motion? So I'm moving to the right, but I push to the left. What happens to the object's velocity? It decreases. The direction stays the same. The only thing that happens is it slows down. Eventually it stops. And then it'll start speeding up going the other way, right? The force is in the opposite direction of its motion. Slows down, stops, speeds up, keeps going. So when a force is parallel or anti-parallel to the direction of motion, the speed changes, the magnitude of the velocity changes. but not the direction.
Say that again.
Yeah. When the force is parallel, anti-parallel to the direction of motion, the magnitude of the velocity changes, but not the direction of the velocity. Which brings me back to this question. What happens when the force is perpendicular to the direction of motion?
Constant.
What's constant?
The velocity.
The
Velocity.
velocity. Velocity is a vector. It has a magnitude and a direction. So which piece is constant, or are both of them constant? I like the idea, I just gotta be more specific, right? For this situation, moving to the right, and I push it to the right, what stayed constant about the object's velocity? The direction. The magnitude changed, but the direction stayed the same. How about if I do this? The magnitude stays the same, and what changes? The direction, yeah. Force is parallel to the motion, change the magnitude of the velocity, but not the direction. Force is perpendicular to the motion, change the direction, but not the magnitude. So I come back and I say, okay, we have a situation where the force is perpendicular to the velocity, which means the direction that the object travels should continuously change, but not the speed at which the object is moving at. Which comes back to my original question. What's the shape of the trajectory? What shape do you get when you travel at a constant speed and continually change direction? A circle. When you have a charged particle entering a magnetic field, it will follow a circular trajectory. The force is perpendicular to the velocity that will force the particle to move in a circle. And then you say, oh no, because the minute that you hear circular motion, you go back to this wonderful thing called centripetal motion. Centripetal motion comes back in. Say, oh, I thought I wouldn't need it again. Oh no, you need it again. So we're going to go back to centripetal motion. A lot of the magnetic field stuff goes back into centripetal motion because charged particles moving in a magnetic field move in a circle. To be continued. We'll see you on Monday. So we'll pick up there on Monday. And this is, if you're thinking about instrumentation, yes, indeed, this is how your mass spectrometer works. Different particles travel on different circles, so you can filter them out. Hey, have a good weekend.